All right. So let's take a deep dive into something that you might think you already get, like time zones.
Yeah.
But even if you've, wrestled with them in your code before, um, I guarantee you there are some seriously weird quirks hiding out in the INA time zone database
Mhm.
that will make you rethink everything.
Right.
We're going deep on the why behind those settings.
Okay.
And we're going straight from the source. An article called Australia Lord Howe is the Weirdest Time Zone.
It's a good one.
It is a good one.
Yeah, this article is fascinating because it takes us like beyond just using time zones to actually understanding the intricate system that makes global timekeeping possible.
Yeah, exactly.
Yeah.
It kind of starts off with a bit of a reality check
Yeah.
for all of us developers out there. It's
Yeah.
basically saying, hey, most of the time you're dealing with the Gregorian calendar, right?
Right. And it even points out some exceptions, like dealing with Japanese driving licenses that use imperial year formats or bank holidays calculated based on the lunar Islamic calendar. But
Good.
for the vast majority of us, it's
Yeah.
Gregorian all the way.
Gregorian calendar check. Got it.
Exactly.
But then the article dives into this concept of mean solar time. Can you break that down for us?
So mean solar time is essentially the average time it takes for the sun to return to its highest point in the sky each day.
Okay.
It's the basis for how we define a day.
Gotcha.
And Greenwich Mean Time, or GMT, was all about measuring that mean solar time at the Royal Observatory in Greenwich, England.
So GMT was like the OG global time standard.
Pretty much.
Yeah.
You could say that.
Yeah.
But these days, it's mostly been replaced by Coordinated Universal Time, or UTC. It's basically like a more precise and internationally recognized version of GMT.
Okay, so UTC is what everything syncs to.
Right.
But then there's this whole thing about leap seconds.
Ah, yes. The Earth's rotation is gradually slowing down,
Okay.
which means our days are actually getting a teeny bit longer over time. To compensate for this, we occasionally add a leap second to keep our clocks in sync with the Earth's rotation.
And this is where things get a bit tricky for us, right?
Well, the good news is, as the article points out, leap seconds aren't usually a major issue for developers. Most systems use a technique called leap smearing to handle them.
Okay.
And here's how the article explains it.
Okay.
Programming languages don't support 61-second minutes, so we smear the leap second by slowing down the clock slightly. This keeps us in sync with other systems while avoiding code breaking down.
Got it. So it's like our systems are subtly adjusting to this extra second without us even noticing.
Exactly. It's a clever way to handle a potentially messy situation.
Okay, so we've got the basics of UTC and leap seconds down.
Right.
But where do time zones come into play?
Time zones are essentially offsets from UTC,
Okay.
reflecting the fact that different parts of the world experience noon at different times.
Makes sense.
Most time zones are a whole number of hours ahead of or behind UTC.
Okay, but then the article throws us a curveball with Asia Kathmandu.
Right. Kathmandu is a great example of how time zones can get a bit quirky. Instead of a whole hour offset, Nepal, which uses the Asia Kathmandu time zone, is 5 hours and 45 minutes ahead of UTC.
So how does our computer even know to handle that?
That's where the INA time zone database, or ZDB, comes in.
Okay.
It's like a giant encyclopedia of time zones containing all the rules and offsets for every corner of the globe, and it all lives as files right on your system.
And these files are written in some kind of secret code, right?
It's not exactly a secret code,
Okay.
but it is a specific format called Time Zone Information Format, or TZIF. And for Kathmandu, the article shows us this little snippet from its TZIF file,
Okay.
plus 054555.45.
Wow, so that's it. That one line controls the entire time zone for Nepal.
It's the beauty of the TZB. It boils down complex timekeeping rules to these concise strings.
Right.
In this case, the plus 0545 is the designation for Nepal's time zone.
Right.
And that MECTA 5.45 means that UTC is 5 hours and 45 minutes behind Nepal's time.
So we've got these time zone designations,
Right.
PST, EST, things like that.
Yeah.
Yep. But the article mentions something interesting about them.
It
does, like they're not always unique. For instance,
Right.
CST appears in 66 time zones. Only 33 of all zone designations are unique.
It can get confusing.
Wait, so multiple time zones can share the same designation? That seems like a recipe for disaster.
It can be if you're not careful. It definitely highlights why it's crucial to be specific when working with time zones in your code. You can't rely on those designations alone.
So what should we use instead?
You should always use the full time zone identifier like America Los Angeles or Asia Kathmandu to avoid ambiguity. And speaking of potential confusion, let's talk about daylight saving time, or
Right.
DST.
Ah, yes, the part where time zones get really interesting and potentially a nightmare for developers.
Exactly. The way DST transitions are handled in the TLARI is a whole other level of complexity.
Yeah, so how does this DB even represent these DST shenanigans?
So it uses a specific syntax within those TZIF files.
Mm-hmm.
The article gives us a great example using Europeans.
Okay.
ET2 East, M3.5.03000, 10.5.04.
Okay, that's a lot to unpack. What does all that even mean?
Let's break it down piece by piece. The ET2 part tells us that the standard time in Athens is called ET, and it's 2 hours ahead of UTC.
Gotcha.
The EST is the name for daylight saving time in Athens.
Okay.
And since it doesn't have an explicit offset, it's assumed to be 1 hour ahead of the standard time, meaning it's 3 hours ahead of UTC.
Okay.
So that's the first part of the string.
Right.
What about all those numbers and slashes?
Yeah, what about those?
That's where the DST transition rules come in.
Right.
The M3.5.03 part tells us when DST starts in Athens. The M3 means it starts in the third month, March.
Okay.
The .5.0 means it starts on the last Sunday of the month.
Okay.
That 5A is a shorthand for last instance within the TZIF syntax.
Got it.
And the 3FET means the transition happens at 3.0 a.m. local time.
Wow, so they're really specific about when that switch happens.
Absolutely. And the second part, M10.5.04, follows the same pattern to tell us when DST ends. So in Athens, DST ends in the 10th month, October, on the last Sunday of the month at 4:00 a.m. local time.
Okay. I'm starting to see how this TZIF language works. It's like a mini programming language just for time zones.
You could say that. And it gets even more interesting when you consider that not all time zones base their DST transitions on the Gregorian calendar.
Wait, what? There are time zones that don't follow the typical DST rules.
There are a couple of fascinating examples highlighted in the article. Africa Casablanca in Morocco and Asia Gaza base their DST transitions on the lunar Islamic calendar.
That's incredible. But how does the DAB even handle that? The lunar calendar doesn't line up perfectly with the Gregorian one, right?
Exactly. The solution, as the article puts it, is the dumbest possible one.
Okay, now I'm really curious. What do they mean by dumbest?
It turns out that TZIF files can contain both hard-coded historical transitions and rules for calculating future transitions.
Okay.
For most time zones, those rules are used to figure out when DST starts and ends. But for Morocco and Gaza, the Stevie maintainers basically said, forget the rules, we're hard-coding it.
So they manually calculated all the DST transitions based on Ramadan for years to come.
That's exactly what they did. And the article mentions that they set a cutoff year of 2086. So until then, Morocco and Gaza's DST transitions are all predetermined and baked right into the STBB.
Wow, that's some serious dedication.
It really highlights the effort that goes into keeping the STBB accurate and up to date. But believe it or not, that's not even the weirdest DST quirk the article uncovers.
There's something even weirder than hard-coding DST transitions based on the lunar calendar. I'm almost afraid to ask.
Let's talk about American Nook.
Nook, isn't that in Greenland? What's so special about it?
Greenland is part of the European Union's DST system,
Okay.
meaning they try to synchronize their DST transitions with the rest of Europe. But here's the catch. Greenland is geographically quite a bit west of mainland Europe.
So their standard time is actually quite different from places like Lisbon or Paris.
Exactly. Lisbon's standard time is UTC,
Right.
while Greenland's is 3 hours behind UTC, but they still want to have that synchronized DST switch with Europe.
So how do they pull that off? Does time just magically bend in Greenland?
It's not magic, but it's definitely a clever workaround. The article shows us the Nuke entry in the TGB,
Okay.
NUNIP 022-1 and 3.5.01000 10.5.00.
Okay, I see the familiar DST transition syntax,
Yeah.
but what's with that Noka one?
That Noka one is the key to the whole thing. Instead of having the DST transition happen at 2.0 a.m. like many other European time zones,
Right.
they shift it to Noga 1.0.
Negative 1 o'clock. Does time go backward in Greenland?
Not exactly, but it's a bit like sneaking the transition in a little early. The way the rule is encoded, DST in Nuke technically starts on a Sunday. But because of that Noka one, it actually happens at 11:00 p.m. on the Saturday before.
So it's like they're bending the rules of time just a little bit to stay in sync with Europe.
Precisely. And the article even speculates that this might be why American Nook is sometimes omitted from certain versions of the TV. It's just too weird for some systems to handle.
It's almost like Nuke is in its own little time warp.
In a way, it is. But Nook isn't the only one playing games with DST transitions. America's Santiago and Africa Cairo also have some peculiarities.
What do they do?
They both have DST transitions that occur at 24.0.
24.0, but isn't that technically the next day?
Exactly. It's as if they're pushing the change into the following day.
I'm starting to see why the article calls time zones weird.
And we haven't even gotten to the weirdest one yet.
Wait, there's something even weirder than a time zone that transitions at midnight of the next day. I can't imagine what that could be.
Get ready, because we're about to enter the realm of Australia Lord Howe.
Lord Howe Island. That name rings a bell. Isn't that the tiny island with that incredible rock formation, Ball's Pyramid?
That's the one, a truly stunning sight. But what makes Lord Howe Island truly stand out in the world of time zones is its DST transition.
What could possibly be so strange about a DST transition? They either spring forward or fall back right.
You'd think so, but Lord Howe Island decided to do things a little differently. Instead of the usual 1-hour jump, they have a 30-minute DST transition.
Wait, you're kidding, right? A half-hour time jump?
I'm completely serious. Their standard time is 10 hours and 30 minutes ahead of UTC, and their DST time is 11 hours ahead.
So twice a year, the clocks on Lord Howe Island jump forward or back by just 30 minutes.
That's right. And as you might imagine, this has some interesting implications for developers.
I can only imagine the headaches this must cause.
The article points out the impact on things like cron jobs that run on an hourly basis. In most places, every 60 minutes you're back to the same spot on the clock. But on Lord Howe Island...
On Lord Howe Island, that 60-minute cycle gets completely thrown off by that 30-minute DST jump. Their cron jobs would be staggered relative to the actual time.
Exactly. It's like Lord Howe Island exists in its own little time warp.
And the article mentions some other fascinating details about the island too, right?
It does. Did you know that Lord Howe Island has a population of just 382 people?
Yeah.
And to preserve its natural beauty, they limit the number of tourists to just 400 at any given time.
Wow, that's incredibly exclusive. It sounds like a true paradise, but I bet dealing with their time zone is anything but paradise for developers.
You got that right?
So after all these wild examples, what are we supposed to make of this whole time zone saga? It feels like there's a method to the madness, but it's hard to wrap my head around it.
Yeah, you know, at their core, time zones are just data.
Okay.
And the CDB provides a structured way to represent that data.
Yeah.
It boils down to a few key elements for each time zone.
Right.
An ID like America Los Angeles's, a set of hard-coded historical transitions, and a set of rules for handling future transitions.
Even with all these crazy variations, there's an underlying system that makes it all manageable.
Exactly. And once you understand those elements, you can pinpoint any specific moment in time, no matter how strange a particular time zone might behave. You've got the offset from UTC, the designation, and whether or not DST is in effect. Put it all together, and you have a unique identifier for that point in time.
It's like solving a time-bending puzzle, but at least there are rules to the game.
Right. And the article does a great job of reminding us why this matters for developers. Every time you convert a timestamp to a human-readable string, you're relying on the CDB to be correct. Every time you schedule a cron job, you're assuming that the CDB's rules will be applied accurately.
Yeah, it's easy to take time zones for granted until something goes wrong. And then it's like, wait, why is this task running at the wrong time? Or why is this meeting showing up an hour late?
Exactly. So the next time you encounter a time zone issue in your code, take a deep breath and remember that the CDB is your friend. It might seem like a bizarre labyrinth at times, but there's a logic to it.
This has been a wild ride. We've gone from the basics of mean solar time to the intricacies of the TCB and even uncovered some truly mind-boggling DST quirks.
Yeah, and what's so fascinating is that even though we often think of time as this constant universal thing, you know, it's actually incredibly nuanced and influenced by all sorts of factors from geography and astronomy to politics and cultural practices.
And as developers, we have to be aware of those nuances, especially when our software operates across different time zones.
Absolutely. The article leaves us with a thought-provoking question.
Okay, shoot.
What happens when a country makes a last-minute DST change? Or when a country decides to abolish DST entirely? Or when a country decides to introduce a half-hour DST shift, just for the fun of it?
Okay, that last one is a bit of a joke, but it highlights the fact that time zones are constantly evolving.
Exactly. The STB is a living document always being updated to reflect the ever-changing landscape of global timekeeping.
So as developers, we need to stay informed, keep our code up to date, and maybe even embrace a little bit of the time-bending weirdness along the way.
Well said.
And on that note, we've reached the end of our deep dive into the weird and wonderful world of time zones. Hopefully you've come away with a newfound appreciation for the complexity that goes into making sure the world runs on time.
Or at least as close to on time as we can manage.
Exactly. Thanks for joining us, and until next time, happy coding.